Welcome to Mystery and Quest, the world of science, where we take deep dives into the science and technology shaping our future. Today, we're embarking on an exciting journey into the complex and fascinating world of artificial intelligence. Have you ever wondered how AI works, how it thinks, and what makes it capable of processing vast amounts of information? More importantly, have you thought about the immense heat these systems generate and how engineers are working tirelessly to keep them cool? Stay with us as we unravel the mysteries of AI and explore the cutting-edge technology that ensures these systems run efficiently. Artificial intelligence AI is a field that has been evolving at breakneck speed, impacting nearly every aspect of our lives. We interact with AI every day, whether it's through virtual assistants like Siri or Alexa, personalized recommendations on Netflix or YouTube, or even the way our social media feeds are tailored to our interests. But how does AI manage to do all this? To truly grasp how AI works, we must first understand its foundation. At its core, AI is based on algorithms, mathematical models designed to carry out specific tasks or solve complex problems. These algorithms don't just operate in isolation. They learn from data, refine their approaches, and improve their accuracy over time. This ability to learn is one of the defining features of AI. Unlike traditional software, where each task must be explicitly programmed, AI can train itself by analyzing vast amounts of information, recognizing patterns, and making decisions based on those patterns. Take facial recognition technology, for instance. It doesn't just scan your face and instantly know who you are. Instead, it compares your facial features to millions of other faces stored in a database, identifying unique markers such as the distance between your eyes, the shape of your nose, and the curve of your mouth. This process is a sophisticated application of machine learning, which allows the AI system to become better at recognizing faces the more it's exposed to different images. So, how does AI get from data to decisions? This is where the concept of neural networks comes into play. Neural networks are designed to mimic the way the human brain functions. Imagine your brain as a vast network of neurons, each connected to thousands of others. These neurons work together to process information, make sense of the world, and help you make decisions. Similarly, in artificial neural networks, there are layers of artificial neurons, or nodes, that work together to analyze data. The first layer of a neural network takes raw input data. This could be images, text, or any other form of information. As the data passes through each successive layer, it is refined and analyzed in greater detail. The deeper the layers, the more complex the analysis becomes, which is why these networks are known as deep learning models. For example, when processing an image, the first layer might focus on basic features like edges and colors, while deeper layers identify more complex shapes, objects, and even specific faces. It's this intricate process that allows AI to perform such a wide range of tasks, from diagnosing diseases in medical scans to understanding natural language in virtual assistants. The more data the neural network is trained on, the more accurate and effective it becomes. But this power comes at a cost. Deep learning models require enormous computational resources, especially as they are scaled up to handle larger data sets and more complex tasks. And this brings us to a critical challenge faced by AI developers: managing the immense heat generated by these systems. To understand why cooling is such a crucial aspect of AI, we need to consider the sheer amount of computational power required to run advanced AI algorithms. Deep learning models, for instance, can consist of millions, if not billions, of parameters that must be processed simultaneously. This requires powerful GPUs, graphics processing units, and specialized hardware known as TPUs, tensor processing units, to handle the heavy lifting. However, as these processors work to crunch massive amounts of data, they generate a tremendous amount of heat. If this heat isn't properly managed, it can cause the system to overheat, leading to reduced performance, potential data corruption, or even permanent damage to the hardware. For AI systems that are used in mission-critical applications, such as autonomous vehicles or medical diagnostics, these risks are simply unacceptable. In traditional computer systems, Cooling is typically handled by fans or heat sinks that dissipate excess heat into the surrounding air. But for high-performance AI systems, these standard methods aren't sufficient. The sheer density of the processing units and the intensity of the computations require more advanced cooling techniques to ensure that the system runs smoothly. One of the most effective cooling methods for AI systems is liquid cooling. Instead of relying on air to remove heat from the system, liquid cooling uses specially designed fluids that can absorb heat much more efficiently. These fluids are pumped through small channels that are built directly into the hardware components, such as GPUs and TPUs. As the liquid circulates, it draws heat away from the processors and carries it to a radiator, where it is cooled before being recirculated back into the system. Liquid cooling is particularly useful for data centers that house thousands of AI servers running complex deep learning models. By reducing the temperature of the system more efficiently than air cooling, liquid cooling not only prevents overheating, but also allows the system to run at higher performance levels for extended periods. In some cases, even liquid cooling isn't enough. For the most demanding AI applications, immersion cooling is being explored. In this method, the entire AI system is submerged in a non-conductive cooling liquid. This allows for direct heat transfer from every component in the system, significantly increasing the efficiency of the cooling process. The use of immersion cooling is still in its experimental stages, but it holds great promise for the future of AI technology, especially in environments where energy efficiency and system longevity are critical. As AI continues to evolve, so too will the challenges of keeping these systems cool. Researchers are already looking ahead to the next frontier in cooling technology: quantum cooling. Quantum cooling techniques leverage the unique properties of quantum mechanics to achieve unprecedented levels of cooling efficiency. While this technology is still in its infancy, the potential applications for AI are vast. Imagine AI systems that can process vast amounts of data while remaining cool with minimal energy consumption. In addition to quantum cooling, there's a growing emphasis on developing sustainable cooling solutions. AI systems are notorious for their high energy consumption, and as AI becomes more prevalent, its environmental impact cannot be ignored. Scientists are working on innovative ways to reduce the carbon footprint of AI systems, including using renewable energy sources to power data centers and designing more energy-efficient hardware. Artificial intelligence is transforming the way we live, work, and interact with the world. But behind every smart algorithm and every AI-powered device lies a complex system of hardware and software, all working in perfect harmony. As we continue to push the boundaries of what AI can do, we must also innovate in how we manage the heat generated by these powerful systems. From liquid cooling to quantum mechanics, the future of AI will depend as much on our ability to cool it as on our ability to code it. Thank you for joining us on this deep dive into the fascinating world of AI. Don't forget to subscribe to Mystery and Quest, the world of science, to stay up to date on the latest scientific discoveries and technological advancements. Until next time, keep exploring the unknown